Hi guys, welcome back to lesson 2 of chapter 1. Does it have to be a right triangle, which is basically continuing to prove whether the Pythagorean theorem has to work for a right triangle, and if not, why? So this is going to be further understanding the Pythagorean theorem. We're on to lesson 2, and while we prove that, we're going to be focusing on two main goals. Understand the conditions of whether the Pythagorean theorem could be applied, is able to solve simple problems with the Pythagorean theorem. So, as our introduction, do you know what method the ancient Egyptians used to create right triangles? Well, you're probably not. So, here was their method. So first we on a rope, this is gonna be a rough drawing of what the just like a random rope about say this way right here. And use 13 equally spaced knots to divide a rope into 12 equal lengths. So that would be, let's see, 1, 2, and then like so on. It will have knots to divide into 12 equal lengths. A craftsman holds the first and 13th knots of the rope at the same time. So basically right here you're gonna add all the knots right here, and then you're gonna like tie them together, so it's gonna be a loop. Now if you stretch it, it's gonna become a right triangle. Well, exactly how? Notice that this is equal lengths. So a craftsman holds the first knot and the 13th knot and just stretches them out at the same time, and two other assistants hold the fourth and ninth knots respectively. So then one would pull back the fourth knot, another one will pull back the ninth knot. Then if they just stretch it out until it's just straight, they will get a right triangle with the right angle at the first knot. So it would look like this, just like that. This is what the loop will transform into. So this would be the first knot, and notice the first and the 13th knots are like overlapping each other because they knot each other. So then right there, one assistant holds the fourth knot while this one holds the ninth knot. They stretch it out. It's a right triangle. So from that, we can learn about the inverse theorem of the Pythagorean theorem. First, let's review the Pythagorean theorem. And that would be, yes, you can say it along with me, a squared plus b squared equals c squared. So now let's do a quick little investigation. The following three sets of numbers are the three sides of a triangle, A, B, and C. And here are three sets. Answer the following questions. 1. Do these three sets of numbers satisfy a squared plus b squared equals c squared? And 2. Take the number of each group as the three sides to make a triangle and measure it with a protractor. Are they all right triangles? Alright, so I'm going to give you a few minutes to answer both of these questions, and we'll come back and look at them together. All done? Well, let's first answer the first question. Do the sets of numbers satisfy a squared plus b squared equals c squared? Well, let's do over here. If you square 5, that's 25, and you square 100, and you square 12, that's 144, and then you add them, so then that would be 169, and that, yes, this is the Pythagorean theorem. And you basically just do this for all of these, and then you will see that yes, they do satisfy the Pythagorean theorem. and to take the number of each group as 3 sides to make a triangle and measure it with a protractor. So, right here, we cannot measure it on a screen with a protractor, but if you can grab a piece of graph paper if you have it, and then, put the, make a triangle with a side of 5 units, 12 units, and 13 units. And then if you do have a protractor at home or some sort of other ruler, you can see if it is a right triangle. So there you go. And here are the experiment results. 1. 5, 12, and 13 satisfies a squared plus b squared equals c squared and is a right triangle. 7, 24, 25 also satisfies a squared plus b squared equals c squared and is a right triangle. And so is 8, 15, and 17, which is the Pythagorean Theorem as well. So as you can see over here, they are all right triangles, and if we use a protractor to come and measure them, they are all, sorry, this is a bit out of place right here, but they are all 90 degrees. So can you find any conclusions from the questions above? So if a triangle's 3 side lengths, A, B, C, satisfy a squared plus b squared equals c squared, then this triangle has to be a right triangle. Well, is this true? Or maybe it's not just a right triangle. Well, that's what we're going to ponder today. Some students think there may be errors in measurement results and disagree with this finding. Do you think this finding is correct? Can you give a more convincing reason? So this is where we're going to be investigating throughout the rest of this lesson. Does it have to only apply to right triangles, or if a triangle side's length does satisfy this, does it have to be a right triangle? So here's some proof. Given, as shown in the picture, triangle A, B, C sides are A, B, and C. It satisfies the Pythagorean theorem. And we have to prove if triangle ABC is a right triangle. Now, I encourage you to just copy this figure right on your notepad right now and just, look at it for a moment. What can you do? What's maybe one way you could solve it? And if you have a different way from what we're telling you in this lesson, in the slideshow, then please share it in the comments down below. We're really excited to read what you thought. All right, let's look at this. So, is angle C a right angle? We don't know. So, well, we don't know if this is true, but if it is true, we know that triangle ABC is a right triangle. So we can first construct right triangle A prime, B prime, C prime with two legs A and B. So, and we can construct it so that triangle ABC is congruent to triangle A prime, B prime, C prime. So let's look at this process together. So first what we're gonna do is we're gonna draw right angle MC1N. So here's what I mean. First we're just gonna draw an infinite line called C1M right here. And then we're gonna draw another perpendicular line called C1N that's perpendicular to C1M. And we are gonna declare that it is a right angle. We're just gonna declare that. No rules, we're just going to declare that. Then we're going to plot C1B1, which is a line segment, on C1M. So right now we're going to take the measured lengths of CB and AC, and we're just gonna borrow them over here to put on C1N and C1M, just like that. And notice how it only said that their lengths are the equal. We never said that the angle was the same. Then we are going to connect A1 right here. Let me point that out. A1 to B1, and then what we're going to do, we're just going to connect them. So in right triangle A1, C1, B1, using the Pythagorean Theorem, we can get that A1, B1 square is equal to A square plus B square, which is also equal to AB. So A1, B1 equals AB. So triangle ABC is congruent to triangle A prime B prime, not A prime B prime, A1, B1, C1, which using the SS rule of congruent triangles we learned last year. So then angle C is equal to angle C1, which is 90 degrees. So triangle ABC is a right triangle. Now let's just quickly review what we have gotten over here. So first what we did was we drew two lines that were perpendicular to each other, and we just declared that it was a right angle where they met and it was perpendicular. Then what we did was we copied down the lengths of B and A, we just put them over here, and then we declared that this was a right angle. Now we have to prove that this is a right triangle. So basically what we need to do is we need to prove if C is equal to A1, B1. So then we use the SS rule of congruent triangles, which we learned last year. I'll put the link in the description below if you need to check that out. So using that, we learned that triangle ABC is a right triangle. So here's the conclusion. The inverse Pythagorean theorem is that if the three sides of a triangle at A, B, C satisfy A squared plus B squared equals C squared, then this triangle must be a right triangle. This is something that is worth copying down in your notepad right now, because it is something very crucial for solving word problems in the future. Alright, and here's the explanation. The inverse Pythagorean theorem is a proven method, that is, if the length of each three sides of a triangle is known, then the sum of the leg squares equal the hypotenuse's square. It can be concluded that the triangle is a right triangle, with the angle opposite from the hypotenuse as a right triangle. So basically what it's saying is if the three sides of a triangle ABC satisfy the Pythagorean theorem, then this must be a right triangle. So here's one practice. Example 1. The shape of a part is shown in figure 1. This is figure 1. According to the regulations, both angle A and angle DBC, let me just quickly circle and mark up those angles that's talking about right here. These two angles, you know what? Here. This angle and this angle should both be right angles, and it should be right angles. The worker measured the lengths of each side of this part. So the worker measured the lengths of the side of this part, and as in shown in figure 2. Now we're asking this, oh, by the way, figure 1's part and figure 2's part are the same part. So now we're asking, does this part meet the requirements of these being right angles? Well, let's do this together. Let's first check angle A. So we know that one leg is 3, another leg is 4, and the hypotenuse is 5. And remember, the inverse Pythagorean theorem says that if these apply to the Pythagorean theorem, then this has to be a right triangle. So now let's just see if it applies. 3 squared plus 4 squared would be equal to 9 plus 16, which is 25, which is also equal to 5 squared. So then, yes, this does apply to the Pythagorean theorem. So we already know that angle A is the right triangle. Now let's do the next one. one leg is 5, another leg is 12, and the hypotenuse is 13. So 5 squared plus 12 squared is equal to 25 plus 144. And that is equal to 169. And 169 is equal to 13 squared. So it also means that angle DBC is a right triangle. So this is what it's all like all together. It says in triangle ABD, AB squared plus AD squared is equal to 3 squared plus 4 squared, which is equal to 25, which is also equal to 5 squared, which is equal to BD squared. So triangle ABD is a right triangle, and angle A is a right angle. In triangle BCD, BD squared plus BC squared is equal to 5 squared plus 12 squared, which is equal to 169 is equal to 13 squared, which is equal to CD squared. So triangle BCD is a right triangle, angle DBC is a right angle. Therefore, this part reaches the requirements. Now we're going to learn about a concept called Pythagorean numerals. Concept learning. If the three sides of a triangle AB satisfy AB, this should be added another one right here, ABC, satisfy A squared plus B squared equals C squared, then the triangle must be a right triangle. The three it's positive and it's integers, which means this is plus positive greater than 0, and integers is whole number. As the side lengths that satisfy A squared plus B squared equals C squared are called Pythagorean numerals. So basically, the three numbers in one set of three side lengths of a right triangle are called Pythagorean numerals. So here are some common Pythagorean numeral sets. 3, 4, 5, 5, 12, 13. Both of these actually are the ones that we've met throughout these lessons. 6, 8, 10, 7, 24, 25, 8, 15, 17, 9, 40, 41, 10, 24, 26, etc. So actually there is no point in memorizing all of these sets, because later as you solve more of these problems, you'll find that there is a pattern to this. So here's the nature of the expansion of Pythagorean numerals. A set of Pythagorean numerals is expanded by the same multiple of k, and a new set of numbers is obtained. This set of numbers is also Pythagorean numerals. So here's how Pythagorean numerals sets expand. And this is example 2. The following set that is Pythagorean numerals is, so which of these are Pythagorean numeral sets? Alright, so first, let's eliminate some things. If you check this out, you just know that this is not it. Remember how I said positive integers. Positive integers. So then C would be disqualified, and so would be D, because it's not an integer. Then the answer would be A. So here's the key point right here. According to the definition of Pythagorean numerals, the number of Pythagoreans must be a positive integer. So decimals are first and included. Then calculate whether the square of the hypotenuse is equal to the sum of the squares of the two lengths. That's just another way you could check. So here's our class summary. Does it have to be a right triangle? Well, we learned about the inverse Pythagorean theorem, which says that if the three sides of a triangle ABC satisfy the Pythagorean theorem, then this triangle must be a right triangle. And we'll also learn about Pythagorean numerals, three positive integers that always apply to A squared plus B squared equals C squared. Two skills we learned: understand the conditions of whether the Pythagorean theorem could be applied, is able to solve simple problems with the Pythagorean theorem. So we have finished proving the Pythagorean theorem, and next time will be all on the appliances of the Pythagorean theorem.